Yeah, okay.
Record and I'll record this.
You will record. Then I cannot make any jokes.
No.
Because you start to laugh and I was really thinking it completely innocent. But then I see that you don't think it innocent. Okay. Like, try to please read this part, why I'm subtracting some part from the original Landau, Ginzburg-Landau formula. So I'm subtracting this part of the energy. And this is for the reason because creating magnetization, M, in the external magnetic field costs the energy. This energy should need to be paid to the laboratory because laboratory is providing the current. Okay? But since we don't care about that, we are subtracting this energy. Here once more the logic is, if I want to create magnetization M in the coil, which is running by the constant current and producing external magnetic field, this is the amount of energy it will cost me. Okay? But someone else is paying for this current, so I don't need to worry for this, okay? So that's why I'm subtracting this. Or how I to say it, it's easier for the superconductor to do the job because there is already existing magnetic field, so he can use the energy from this magnetic field to create itself as it wants. So he is using the energy already from the existing magnetic field, and the energy which was used is not taken from nothing, it is taken from the current and someone else is paying for the current. This is only, I just want to tell you, this would be only important if you would like to interpret some results. It would not be important to find the minimum of this functional. Whether I will have this extra term or not, final equations will not change. But the interpretation of the solutions will change. Okay? So let's do it like that. I will post it today on the Moodle, or tomorrow latest with the homework sheet. I will maybe prepare more problems and maybe we can then discuss next week these more problems that you can learn something, okay? And then just want to tell you, okay, so I explain you why we are subtracting this term, or I hope I explain you. So if you are subtracting it and you are putting it under the integral, then if you want to put it under integral and you want to put it in the most general form, because I was considering the special case that the magnetization is perpendicular to the magnetic field, but if it would not be, then what will happen here? It would be the vector product. Okay? Oh, vector scalar product. Yeah, instead of Bxm, there would be vector scalar product, and this V is dV. Yes, so I'm just putting inside of that. And normally people are still a little bit rewriting it, because the external magnetic field, and this is the magnetization. Magnetization is the difference between the actual magnetic field and the external magnetic field. You know, so I can write this term as I'm doing like here. So it's a B, which is curl of A, minus B external, which is B external, mu 0. So instead of this M, I am writing like that. So this is the free energy which you can find in many textbooks. Okay? Fine? Or confusing? Give me some signal. I see now you are confused. Nothing? Who is confused? Guys, interrupt me, okay? I am very friendly before I am examining you. If I'm examining, I am a beast. I don't know you. You cannot call me Dennis that day. And I am really, but now you can really enjoy that I will to answer, so go and ask me question if it's not clear, okay? Clear? Is it clear? Great. So this is the free energy functional which is logical. This is going to be free energy. And I'm just telling you that some textbooks use this. Some textbooks, for some reason, they also say, oh, but let's also subtract the energy needed to create Bx, because this laboratory field is already created already, so we can also subtract it. That's always just subtracting some constant field. Because Bx is fixed, so I'm just subtracting another term. So some guys are a part of the term which I moved before, they also subtract some another energy of the magnetic field, but the constant magnetic field. Okay? If you then do this, and you again express M as I did before, and you put everything together, you will get this expression. Okay, just look for the mathematics that's basically if I am plugging this M, just look how the M looks like before. M is this. I'm just plugging M here and then you see that I can write it as this thing. Trivial. Even some people, they subtract twice of that energy. So before I had 1/2 here, now I don't have 1/2. That's again constant term, okay? And this is a different convention why people are having here, and in that case, again, it will look a little bit differently, but all this subtraction extra which I'm doing, they are effectively constant, okay? Once the magnetic field is constant and you do the experiment in a constant magnetic field, this does not matter. You are just shifting the level from which you measure something, and it's a global shift, okay? I am just telling you because you can see in the Schmidt book, I will upload today the chapter also. And Schmidt looks differently because he is not using any magnetic permeability because he is working in CGS units. So he has somewhere 4P and 8P and some numbers. This is because he is using different units. But you will see that he is using this. I uploaded before in the Moodle the lecture notes from Professor Zirlin, and Zirlin is using this convention. Okay, so don't worry, it's not a mistake, they only take a different reference of that, and it's a global shift. Okay? You can pick up any you like, you even don't need to pick up G if you don't like it, you can stick with the F, but once you pick it up, then you need to keep that till end of your life, okay? So just pick one, and then you need to make the comparison or just keeping one fixed, okay? You cannot compare just different things. Okay, I will come to that. I don't want to. Okay, you will see what I'm meaning. Okay. So I will derive the equation using F, not G, and as a homework you will see that try by any G, you will see that nothing changes. Okay, I'm just making a few comments that this G is in principle function of the position because the order parameter, which is measuring how much Cooper pairs are distributed in the superconductor and how the vector potential is distributed on the superconductor are depending on the position. So in principle, this is the function of the position, and then I'm making the integral over all position. So this is the local thing and this is the global thing. So this is the energy. And I'm telling you, the nature chooses such configuration of the magnetic field C and the vector potential A or the magnetic field B because they are connected, such that this guy is minimized. Not this guy is minimized. Integral of these guys should be minimized. Okay? That's the other thing which I just want to tell you. And I was telling, and we will do it slowly, we need to know how to minimize this guy because this guy is not a function, it's a functional. So we need to know how to minimize the functional. Okay? So what we will do, we will change psi a little bit. This is arbitrary function. I will change vector potential by small function and we will compute how this functional is changed. Okay? And then the postulate, and this is called the variational principle or the least action principle, is telling you that the nature is choosing such values of psi and r such that this change is a 0. Okay? And this is called variation principle. We will come to that in a moment. What I am telling, okay, and what is important? Okay, we will see that if I use F or G, 1, 2, or 3, the final equation, which is called the Ginzburg-Landau equations, will be the same. This does not depend on that. We will see that these equations are nonlinear. I'm just preparing you. We will see that if you have a partial differential equation which are nonlinear, then you are having several solutions. Since the equations are nonlinear, you cannot make the superpositions. So if you know two solutions, then it does not imply that any linear combination is also a solution. All right, so this is very important. And now comes the thing which I'm always telling you why it is important. If your experiment, if you are calculating your equation, and the guy in the next lab is doing the experiment in the constant magnetic field, and you would like to tell him what he is seeing, or you want to describe his experiment. Now comes this important of G. What do you need to do? You need to find all solutions of the Ginzburg-Landau equations. They are nonlinear. There can be several different solutions. You need to find all of them, and for each of these solutions, and then you pick one GS. Does not matter, 1, 2, or 3. Does not matter. You know that in this GS is also external magnetic field included. Because the guy in the neighboring laboratory is doing experiment in exactly this constant magnetic field, okay? And what you need to do is, you need to calculate this GS for all your solution which you found. And out of all numbers, you just pick up the one which is the lowest one. Do you understand that? You can get more solutions. Yeah, so there is one function of this GS. This GS knows about the external magnetic field. So if you want to describe the situation in that external magnetic field, you need to plug inside all solution which you find, which means do integral, and you get a number. And you get number 1. Then you put different solution, you get number 2. Different solution, number 3, blah, blah, blah. And then you see, oh, the number 3 is the smallest number. So it means this solution is relevant in this magnetic field. It can up that the free energy would not be the minimal, but the Gibbs free energy would be. It can happen that if you take the free energy, in the free energy there is no any external magnetic field. If you will again plug the solutions, because the solutions are the same, you can come get that this guy would be the minimal free energy. So the free energy can be smaller here, but the Gibbs free energy would be smaller here. Okay, and this is the important thing. Did you get me? Should I repeat?
So Gibbs free energy is more suitable than free energy in this situation.
In the situation which you will do the experiment in the external magnetic field, under the condition that the current is kept constant, then you should take the solution which minimizes the Gibbs free energy. Okay?
Because Gibbs free energy consider the external field.
Yeah, exactly. And free energy does not consider it. Okay? So this would be the thing. Okay? This is only just out of the solution which one is the true winner. Okay? So we will solve the differential equation, we will get several solutions, and we need to pick up only one winner, because in the nature, normally there is only one ground state. Of course, if you have a quantum phase transition, you can have more, but this is the classical stuff, kind of. Okay? So there is one winner, and this winner is specified by the value of the Gibbs free energy, which is a number, and this number has a unit in the joule, and you need to pick up the one which is the smallest joule. Okay? Got me? Perfect. So now we need to derive these equations. So what I will do, and you can check it, I will do it from F. You can do it from G. If you want. This would be one homework problem. Pick up any G and try to see that the equation does not matter whether you use S of G or something like that. So I will use the F, and this is my functional, okay? This is the thing which depends. So my F, this free energy density depends on the psi, which is a complex wave function, and depends on the magnetic field, which is hidden here. And this D is this covariant derivative, okay? So what I will do, I will now make the change in the psi, and then the change in the A, and I will derive some equations. And I will bring you for that. So I just want to make, do I have a, okay, so this is the free energy function, I want to minimize it, and I will do the following assumptions that I will assume that, I will change the psi a little bit, I'm saying it, and I will change a little bit, I'm already doing it, and I will assume that the psi can be arbitrary, but the vector potential cannot change on the boundary. Okay, just to again explain you, that's nothing difficult, that's only, I will get this a little bit simpler boundary conditions at the end. Okay. So let's say this is my superconductor, I'm just drawing it, it's lying in the space, so this is like my three-dimensional space, and it occupies some volume V, okay? And now I'm trying to derive the psi. So what I'm doing is that there is a psi, which has some value, And now I am doing a small variation of this psi. I am taking some other function which is a little bit different than my original function. Yeah, so there is a given function psi, and then I am taking the new function which is psi plus delta psi. And this delta psi can change and independently how it is. Okay? I can even allow that it's changing on the boundary. So this is the boundary of my superconductor. It is some two-dimensional surface, but I cannot draw it because I just draw it like that. Okay? Did you get me? Yes? Okay. But for the magnetic field, there is also some magnetic field. Okay, there is also some magnetic field. Okay. And I will also make some variation of the magnetic field. But I will assume that the variation of the magnetic field is like that, that the end is fixed. Because normally the magnetic field should be the laboratory magnetic field. I cannot change it much. Because at the boundary of the superconductor, I am going to the normal, to the vacuum, and on the vacuum, the things are given by the laboratory conditions. So the magnetic field cannot change on the surface. So then I am not changing out. So there will be my assumptions that how I will choose this function. Yeah? They can be arbitrarily, but this one, there should be zero, sorry. Okay, other typo, there should be zero. And what is the logic? Guys, did you remember in the classical mechanics, when you derive the Lagrange equations, you heard something about the least action principle? You had the Lagrangian, and then you make the Euler-Lagrange equations. Did you remember how it was done? What we are doing here are the Euler-Lagrange equations, but for a little bit more complicated problem than in the classical mechanics. And I'm just telling you the story. So I will change my psi and psi star a little bit. I will change my magnetic field a little bit, which means I will change these things under the integral. And my goal is massage this expression in the following way. That I will get a term only like this. This is the original term. And then I will got the contribution which will be linear delta psi, linear in delta psi star. Of course there will be also higher things, but I'm completely not, I'm just going to the linear order. I need to do some massage here, such that I can take out outside of the thing delta psi and delta psi prime. And again, I need to do some massage and I can take out vector potential A. And you will see that on the way, we also get some boundary terms because there are some partial derivatives, and I will turn the partial derivatives to volume. I will can use the Stokes theorem or the Gauss theorem, okay? So on the way, there will appear some boundary terms because I will do some per partes integration. You will see it, okay? But the logic is like that. I put this into the game, and I need to do the massage such that I am getting something times delta psi, something times delta A. Okay? This is the goal. And this variational principle is telling me the following things. That the minimum or the extremum is found when, and this guy has a name. So this thing, there are people denoting by this symbol. So this thing in this expression, it will be some expression that people denoted by this letter. This is delta psi f. And this is called delta AF. This is just the name to give it a bookkeeping, okay? And the minimal equations are satisfied. We will get some differential equations. So we will see that this is some differential equation and we require that this is equal to 0. And this is some differential equation which is equal to 0 and the boundary term should be the 0. So this is the analogy of the following things. If you have a function of x, then you know that you are in the minimum. You know that you are in the extremum. If this function can be written like that, if you write some delta x, then the next contribution, there is something else, and this is delta x squared. So there is not a linear term, right? If you make the expansion. Minimum or maximum means that the partial derivative of f or total derivative of s is equal to 0. This is the definition of the extremum, right? From the mathematical analysis. The definition of the extremum from the functional is also this thing, but it means this. We need to do the expression like that. So their contribution is of the higher order. Did you get me? Everybody, not only talented students. Sam, did you get me? No? Yes or no? 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 So what I should repeat? Which part is problematic?
Explaining part.
Exponential? This one?
Yeah.
No, I'm just saying that this is the analog of the things which we are doing in the. Okay, it's important. So if you are having the function, and I don't love this chalk because it's already broken. So if I have a function x plus delta x, I can expand it to the Taylor series. Etc. Okay, and this is 1 over 2 factorial. If I am doing the expansion around the point x, which is a minimum, then the first derivative is equal to 0. Right? So the necessary condition to find the minimum or the extremum is that the first derivative is equal to 0. So the corrections, the Taylor expansion start from the higher order term. The same thing for the functional. Now I have a functional which depends on some function psi. We would say that function psi is a minimum or maximum of this functional if analog of this is happening, and analog of this is this thing. So we need to massage it and we will see it. Okay, you will see it. So this is like the first order corrections are 0 in analogy with the function of that. Clearer? Maybe you will see how I will do it.
Why after, can you slide? The basic logic and upper.
What do you mean?
The two. And I still don't know what this means.
This?
No. We assume unconstrained.
Oh, you will see it.
Oh, I was okay.
You will see. Okay. So let's start with that. So I have a functional, and you see how this functional looks like. Okay? It has several terms. These terms is just depending on psi and does not depend on a. This also just depends on psi, does not depend on a. This depends on psi and depends on a because in D is hidden a. And this does not depend on psi. Okay? So I will firstly start to do the variation with respect to psi star. Okay? I treat it as an independent variable. So you will see how I am doing it. So let's start it. So this would be my term. I take my term as before, and I a little bit change psi star by some function delta psi star, and I have also this function delta psi star. I made this change. Did you see it? This was original functional, and now I change psi star a little bit. Do you see it? Now my goal is transform this expression to the original expression without delta psi star plus something which has a delta psi star. And ignore everything what is higher order. Fine?
Yes.
Everybody? Great, so I'm doing it, it's super easy. Okay, delta psi, and if I'm doing just this term, it's super easy, right? Because what I'm just getting it is I just need to distribute it. This time this is here, so they contribute to this, and this are here. And I already take it out. Fine? And now I need to do this. So I have psi star plus delta psi to the second power. So I can just use the binomial formula. So it is a psi square plus 2 psi square, psi star, delta psi star plus delta psi star square, but I am ignoring higher order terms. Right? And now I am distributing it. So this time this is here. And this time this is here. Do you see it? Everybody? Perfect. So we get it. That was the task. Start with that and massage it to get this term. So what we'll learn is here. So we learned that the variation of this term, this is called the variation of this term. This is the name. You know, people invented this name. So variation of this term is here. So this is the result. Right? So you just see it. I have 2. This 2 is cancelling this 1/2. So the variation of this looks like this. Did you get me? Guys, some of you, did you have it before? I think you yes, but some younger guys, did you have it? Who has it? Huh?
The first, like the delta size, I mean, the notation,
Yeah, this is just the name. This is called like this is just the name for this. Like when you say that the derivative of the function is 0, you can write it like a partial derivative with respect to x of f is 0. And for variational calculus, the people will denote it like this, that they want to emphasize that instead of such delta, they are writing such delta. This is just the symbol for that. Yeah, I'm apologizing. Maybe it would be better if I will consider not this delta psi as the, because this delta psi is completely something different. Yeah, this delta psi is really, we change the wave function. And this delta psi is just the symbol that we are doing this mathematical operation. It is just the symbol that people look for that, and they, in their mind, they see all this procedure. Ah, this means that I need to do that. Do. So instead of writing it like that, people in mathematics, they created this symbol. Do this. And they know this is the symbol for this procedure. Okay? So this delta psi and the previous, this is just the name of the procedure. Like in mathematics, or I don't know. In Python, you are calling some function which is doing some procedure for you. So this is the function which we are calling. And the procedure is, okay, do this, expand it, ignore higher terms, write it at the end like this. Okay? So the first term we have. Can we go for the next one? Perfect. So we go to the next one. And now we need to also play with the second term. So we are having that there is a term deep psi star, deep psi star. Yeah, this is other term in my free energy. So I need to play with this term. So we are doing the same game. We take the original term and a little bit shift the wave function. So if I change the wave function psi, and now I am making a derivative of the function psi, then I will get a derivative of this change function. Is that clear? Clear, brother? Marcus, is it clear? Great. So I am again now expanding it. So I'm expanding this and this. So I'm getting this original term. And now I am getting the term which looks like this. I need to make the derivative. This is a complex conjugation. So the complex conjugation is jumping here. The complex conjugation is jumping on this function, right? I'm getting it here. And I'm getting the things delta psi. But this guy is not in the form we want because in front of this is this derivative. So we need to do something with that such that we are liberating delta psi out. We will need to do some per partes. Do you remember Euler-Lagrange equation? That's exactly the thing which appeared there. You get a term and then you need to do the per partes. So we were exactly doing this. So now I am gonna to play just with this term, okay? I am gonna to play with this term. Only like that. And just keep in mind that this star is now plus E because it's star. So there was before minus, now it's plus. So I need to play a little bit with this term. So let's do it. So I'm plugging it exactly. So it is E, H bar, nabla acting on the delta psi star, which is some unknown function, but does not matter which one. 2 ER, unknown function delta psi star, multiplied by that. And now comes the trick that, okay, you can separate these to the two parts. This is the first part. This is the second part. Second part is super easy, right? This delta psi is already out, and only those two things match each other. So this part is super easy. Do you see it? I already got delta psi star out. Everybody see it? This delta psi is hidden under the gradient here. So we need to get it out of the gradient. How we will do it? I just remember if the gradient of the product of two functions minus original function and the gradient acting on that. I'm just using these things. Do you see this? Just have a look. I'm claiming that this time this is the same as the gradient on the product minus this. Have a look whether you see it. Do you see it? Everybody see it? Then I'm doing like that. Okay. So then it means that this term and this term are going together here. Okay? And this term survive. Do you see it? But now I'm using the thing that I have something which is the volume integral of the gradient of something. So the volume integral of the gradient of the something, I can turn as a surface integral, and I'm using the Gauss theorem. And this is the Gauss theorem, how it looks like, yeah? So, integral, you know it in the following form. This is exactly the things which you know, only a little bit written, like I have a volume here, and this is the boundary of the volume. People normally denote the boundary of the volume by the symbol delta V. It's just the name for the boundary. Okay? And this integral is the following form, that you are having integral delta V, and then you are having a divergence of some vector A. This integral. And what I am doing is that I am changing this divergence of the vector A to the integral ds times vector A. And even I am writing it like that, that this ds I am writing as a ds times the normal vector times A. Okay? So this ds element I can write as a vector, and I can write it as a true area times the unit vector. Okay? This I did. Is that clear? So perfectly, that's what we get. So look guys what we get. So we are lucky, we were able to liberate, we started from this beast, but we were able to liberate it and get it just out as a function, not the derivative of the function, but on the way we got the boundary term. Okay? So the people will write it like that, that making the variation, so again this is the symbol of the routine which I'm calling in Mathematica. So making the variation of such expression is giving me this, but this is by the way d, original d, and this is d, so together it is dd. So this is this term, plus a boundary term. Okay? Fine? I don't need to do the variation of this guy because there is nothing which depends on psi. The variation, if I will now write it, then I can write it that the variation of this with respect to psi is a 0 because there is not the psi. I cannot vary. I cannot change nothing there, right? It will be like that. Is it clear? Is it clear? Yeah?
Can I say, so we vary for d by dot d by divide 4 and vary this is equal to the right hand side of
Yes?
this.
Yes? Plus the boundary term. Okay? So now the total variation of this functional, which I started for, with respect to psi, which I just wrote all the terms together now, should be equal to 0. This is like this, that we want that like the first derivative of the function in the minimum is a 0. So we would say that the first variation of the functional at some function psi should be 0, and this means this function is the minimum. This is like the least action principle. Okay? This is the same thing. So you see that the variation of this term is at the end. We get from this, it's here. From this, we get here. And this is called the first Ginzburg-Landau equation. And this is written like a little bit. I just really write this d explicitly for you. So there is a times psi, b times psi star psi times psi, and this is just the kinetic energy from the Schrödinger equation. You just see that this is like a Laplacian with minimal coupling. Do you see this? Everybody? Great. And I can call it a non-linear Schrödinger equation because I can interpret this as a kinetic energy. I can interpret this as a potential energy, but there is also a self-interaction. So that's why it's non-linear Schrödinger equation. And then it means why we are not having superposition principle, because this term is non-linear. Okay? Some people call this equation Gross-Pitaevsky equation. Okay? But okay. Gross-Pitaevsky was derived differently for the Bose-Einstein condensate. Ginzburg and Landau did this for the superconductor. So psi is a fermionic field, and in the Gross-Pitaevsky equation, psi is bosonic field. That's only the difference. But the equation looks exactly the same. Only interpretation is different of the psi. One is a bosonic something, one is fermionic. Guys, fine? Good. And what we should get, so we are looking for such solution of psi. Unknown function psi should be chosen like that it satisfies inside of the volume this equation. And on the boundary, it should satisfy this equation. That if I am going to the boundary and I am computing the derivative as given, I should get a 0. Okay, so this is the boundary condition which I derived.
So why boundary it should be here? So,
Well, like if you have a differential equations partial, you need to specify some boundary condition. Otherwise you are in trouble. So this is like the boundary condition which we derived along with that. Okay? Fine? But still there is A. So this equation, any A you choose, you need to solve it. We need to also derive some equation for A. So what we need to do, we need to make the variation of the functional with respect to A. So we need to do this procedure. Okay, this is this term which I'm telling you. This is the mathematical procedure which we are doing. We are making the variational derivative. Some people call it variational derivative. I am doing variational derivative of the functional. You come to the party today evening and say, today we did a variational derivative and the patient survived or he is dead. You know, it sounds so scientific, you know. Or you come to your parents or younger brother and I don't know, they will absolutely don't know what you are talking. Variational derivative of the functional. It sounds so mysterious, okay? But at the end, it just means we just change something by something, and then they just massage under the integral using linear algebra, and sometimes use the per partes or the Gauss theorem. But scientifically, it sounds like that, okay? Perfect, so you come to the TSMC for the interview, say, yeah, I'm doing variational derivatives, and things like that, okay? So we are doing the same thing now, okay? But now we are changing the different thing. Psi is fixed, and now we are changing this guy A. It's a vector, so I need to change it as a vector. So if I'm changing A to delta A, then also D is changing to D plus this guy, okay? I want to finish today this, so maybe I will take 5 minutes more, okay? But still we have 10 minutes, right? Okay, so we do the same trick. Let's look for the functional which we are having. This is our functional. And let's just see where we should be careful. There is not A. I don't need to do here anything. Changing A here does not do anything. So the variational derivative of this term with respect to A is 0. Okay, this is a scientific line. Variational derivative of this term with respect to A is also 0. I don't need to do anything. So A is only hidden here and hidden here. So I need to start with this term and then this term. Okay, so let's start with the first one. Good. So we are starting. So delta A, I'm starting with my original expression and I need to change it here and I need to change it here because there is just one A, so I need to change it here and I am changing it here. Is that fine? This is the starting of the game, is like this. Perfect. Now what I need to do, I just need to do everything what is legally allowed and I just need to pick up delta A outside. Which is super easy. So this time this is equal to this. So this is the original term, which should be always there. And now I just do this. This time this, and this time this. And this time this is delta A squared, which I am ignoring because it's higher order. So I'm just distributing the brackets. Okay, so if I'm just multiplying this times this, I'm getting this term. And if I'm multiplying this times this, I'm this, because there is a star, so I need to put star here. So I'm getting this term. Just those two terms. Just please have a look that you see that I'm not cheating. It could be that I make a typo. If you find it, please remind me. Okay? and delta I is automatically out. Nothing more. So my conclusion is variational derivative with respect to A of this expression is equal to 2A, 2 divided by 4M, and the things in the bracket. All good? Perfect. So first term is easy. And with this term would be a little bit more work, but just a little bit. But we already did that work when I was deriving the London equation, but maybe you didn't pay attention. So again, now I need to play with this work. So if I'm changing A by delta A, then I'm changing curl of A times curl of delta A. And again, you see, now it starts to be a problem because delta A, and there is this differential operator standing enough, so I need to do some trick to get this guy out of the differential operator, which means partial integration is needed, or the Gauss theorem, yeah? This is the indication of this, okay? But still, let's play. So I am now using the binomial formula. So this is this square, fantastic. And now I'm having this time this, time this, time this. This is just the vectors, okay? Plus, and I will get this term to the second power, but it's in the higher order in delta. It's in the second order of delta. I'm not taking it into account, right? So this other term which is here is delta A square, and I'm not taking into account. Is that clear? Perfect. So I'm just having here. So if I'm plugging, then I'm getting this original term, which is boring, and now I am getting term which is this guy and this guy. There is 2. There was 1/2 over 2, so these 2 and these 2 are cancelling, so I'm just having var over mu. And I get now this expression, so there is a curl on A, scalar product curl or delta A. And you need to somehow get out of that, and then I'm just telling you, you can check it, and we use exactly this identity when I derive the London equation. You can check it directly on the list of paper, that this thing can be written as a curl A delta A minus divergence of curl A vector product delta A. Actually, it's not difficult to do it, but I'm just writing it, okay? You can check it by yourself. But this is just trick. And you exactly see, that's a fantastic, because now I am getting what I wanted. Oh, this is this cute term which I was looking for. And here I am getting again a divergence. So getting a divergence, I can again use the Gauss theorem. Okay? So then I'm doing it. So this term, I am not repeating already, because we know it would be here. I'm just playing with this term. So I am getting this contribution. I just wrote it explicitly here. And this is the second contribution. And I already used the Gauss theorem. Okay? Please have a look. Okay, so I'm just writing this term, and I already separated this guy separately, and this guy separately, and I already used the Gauss theorem, so there is the integral over the surface. Okay? And you see what I'm getting. If I'm integrating over the surface, then what would matter is the value of A on the surface, but I was assuming that the magnetic field on the surface cannot be changed, because there is some laboratory magnetic field which is there. So delta A cannot be changed of the surface. So it means this integral is 0. Okay, I even don't need to worry. So I'm not getting any boundary condition, because this delta A is 0 there. So at the end, I just got that it's a curl on A, and the boundary term which is identically 0. Okay? Okay-ish? Everybody? Not that you will come home and say, Mom, he's talking, I'm not understanding him. First of all, he speaks English too fast. His mathematics is brilliant, you know. Everybody understands? Okay? Perfect. So now we can write all that together. So now I can write the functional derivative of f with respect to A, which is this should be equal to 0, because this is the condition which specifies the minimum solution. And I'm just saying it that it's this time this, which I already got it. So this will be the equation which I get. First term which I get before, and the second term which I get now. This term and the term which I get before. Okay? And this equation is called the second Ginzburg-Landau equation. Okay? But by the way, I want to tell you this nothing else is the Ampere law. Because I want to tell you, remember that curl of A is B. So what I'm having here is a curl of B. Okay, so I'm leaving it here, but I just wrote it on the other side. And this guy, just look, I put on the other side, so it's with a minus. So I just doing like that. I put this guy on the other side, so this is a minus. Minus 2e, h bar 4me, and now I explicitly wrote those guys for you. It's a psi, gradient, psi minus, blah, 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 blah. And guys, just look over here. This is nothing else as the particle current density, covariant particle density. From quantum mechanics, you know that if psi is normalized wave function, this is probability current. This is the particle current density. And this particle current density is multiplied by the charge of the Cooper pair, which is minus 2e. So altogether, this is the supercurrent, Js. So what we discover is basically nothing else than the Maxwell equation. 1 over mu 0, curl of B is equal to the current density. Okay? So from the Ginzburg-Landau functional, we derive the Ampere law, which already tells us that this functional is probably something deep, because we discover one of the Maxwell equations. We didn't get some contradiction with it. Okay, so we are not breaking something fundamentally physical, okay? So the geniality is that, okay? Just keep in mind, just plug by yourself and then familiarize, and just remember, normally in quantum mechanics you are having here 2m. But Cooper pairs are having mass of 2 electrons, so it should be 4m. M is mass of the electron, and the Cooper pair has a mass of 2 electrons, so it's a 4m. So it's exactly as it should be. No schwindel. Okay? David, you want to say something? You want to ask? Because we were assuming, I was telling you that this function A is arbitrary variational function. And we were saying we do everything in the bulk, there is no limits on it, but on the boundary the magnetic field is set up by the experimental condition. Yeah? And because of that, we cannot change it on the surface. Yeah. Okay. So we derive 2 equations. Oh, I don't have any more. Oh, I'm so sorry. So we derive 2 very fundamental equations. First Ginzburg-Landau equation, boundary condition, and the second Ginzburg-Landau equation. And these equations should be solved all together. And you see that vector potential, equation for the vector potential is requesting to know something about the wave function, so they are coupled. Dynamics of the A, or the space profile of the, this is not the dynamics because there is no time dependence. This is only spatial dependence. So you see that the profile of the A requests to know how the wave function behave, and the wave function profile, which is given here, this is the profile of the wave function, psi, is also given by the A. So they are coupled. Okay? And this is the reason why the condensate is expelling magnetic field and things like that. The magnetic field and psi cannot be treated independently. They are talking to each other. If one changes somehow, the other should correspondingly change. Okay? So this is the Ginzburg-Landau equation, and next time we will start to solve those equations in very simple geometries. Like we find the critical current, proximity effect, and then is a geniality being that there was a student of the Landau whose name was Abrikosov, Alexei Abrikosov, also Nobel Prize winner. He solved this equation and he discovered vortices. And then the people measure it and they see it. So it was surprisingly like he was showing that the vortices, so these equations are really deep. But it's just pure phenomenology, just things like that. Those guys are just proposed the functional with some order parameter. They put a kinetic term because say that order parameter does not like to change in the space so much. And then they derive some equation. But later when we will solve this equation, we will see that there is deep physics behind, okay? Even better story, later come the microscopic theory, Bethe-S theory, Bardeen, Cooper, Schrieffer. They write microscopic, they write many body Hamiltonian, solve it, they get some equations, There came another student of the Landau, which was called Lev Gorkov, and he from the BCS theory showed that the BCS theory in the limit of semi-classical limit is giving you the Ginzburg-Landau equations. So you know what we did. We started with London. We generalized the London. This is the Ginzburg-Landau. Come BCS, which is even better microscopic generalization. But starting from BCS, we are able to derive Ginzburg-Landau, and we are able to derive London. Okay? Just how we get a London, and this is the last word for today. This is the expression for the current. Superconducting current is given by this expression. Now consider what the London brothers considered, that this psi is just, as we had before, some constant which is not changing times a to the e theta r. Plug it there and you will get the London equation. So the London theory is hidden here. Okay? Beautiful, isn't it? But I am there because this D is for me, you know, so I am already part of the story, but you should make your theory, guys, and should get the famous. Yes, David?
I have a question. That's why we choose the sign conjugate of psi.
Does not matter because we can do the variation also with respect to psi, but what will happen, we will just do the complex conjugation of this equation. So doing it with the psi, we will get the equation which will just the complex conjugate of that. So if this equation is true, that also complex conjugate is true, so we will not get anything new, okay? Keep in mind, this is the complex things, and okay, this is real thing, but this thing is cooked like that even the psi is a complex, all this thing is a real at the end. So E at the gradient, it's chosen like that only real part survive at the end, okay? But the first equation, this nonlinear Schrödinger, is a complex equation. It's a scalar equation, this is just the scalar equation, but this is the vector equations. You see that it's a vectorial equation, current, and you are seeing the gradient and they are having vector symbol. So it's free equation in a sense, okay? Or one vectorial equation. Okay, that's it. Well, let's call it a day.
Okay. 谢谢 Nice.
Okay, we can now discuss.